you have a k-dimensional vector space of Rn, and it's you have to show that this is a manifold that is diffeomorphic to Rk, and that all linear maps on V are smooth, right? And then you say if you have linear isomorphism for Rk to V, right? So if you like, the first step is to show that there is a diffeomorphism from this subspace to Rk. Now you say you have linear isomorphism between Rk and V. Then the corresponding coordinate functions, the coordinate, what is it? The smooth functions in there would be linear functionals on V. Linear functionals on V called linear functionals. I'll have to check that.
That's a small typo. It should be called linear coordinates.
Linear coordinates, right? Sorry.
So my thought on this one was, why don't we choose an orthonormal basis for Rn, where the first k vectors are in V, and the remaining vectors are orthogonal to V.
Okay.
And then our map into V will just take A1 through AK to the sum A1 V1 plus blah 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 plus AK VK.
Okay.
And then that's a linear map from RK into V.
Right.
So we've covered V with one parameterization. And then for the reverse map, I don't know exactly how you define it from V alone, but we could define it on all of Rn just by projecting onto. You could do it all with dot products, basically. So you take a vector in Rn and dot it with E1, our first basis vector. And we do that for the first k basis vectors. So that maps all of Rn into Rk. And the restriction of that to V is the inverse of that parameterization. So that those are the corresponding coordinate functions are just dot products with the EIs.
Right. So those would be, like, if you remember what linear.
Since they're linear, they're smooth.
Right. So those would be the linear functionals. It's like, the.
Yeah.
I don't know. I think like it makes linear functionals make more sense when you talk about it in terms of bilinear forms, but like a dot product is a bilinear form, so.
Yeah, he never defined what linear functional meant, though, right?
He assumes you know basically algebra.
But basically, dotting with EI is the same as feeding the vector to DXI, or the corresponding one form.
Right.
I guess the dual one form.
Right, the covectors.
Yeah. To me, that kind of feels complete. I just didn't take the time to type it.
Yeah, that's pretty much what I thought too. But I'm not sure about others. Gunjit, are you comfortable with the kind of approach that I talked about?
You explain like the second part
about the linear functionals?
Yeah.
Yeah, I was rambling a little bit. My thought is that if we form an orthonormal basis for Rn, where E1 through Ek span V, and then the remaining vectors are orthogonal to V, then we can form a map from all of Rn to R just by dotting a vector with E sub I, where I is between 1 and K.
Mm-hmm.
So
Okay.
those are going to be, those are smooth on all of Rn. So their restriction is going to be a linear smooth map on V itself. And that's going to be the inverse of the mapping that we gave from RK into V. So basically the coordinate functions are given the
So is it like kind of projections of
yes,
R
it's
into R?
exactly 100% projection.
Sorry, your voice gets like mumbled a bit.
Yeah, I think I might have some background noise here too.
Oh, yeah.
But you're right. I'm just using dot products to do the projections.
Okay, okay. Yeah, got it.
Right, and if we try to look at, try to write a proof of it, I'm not sure. I think it can be a good exercise to write a proof live. Um, I don't know if people are interested. I can write a proof, but, um, I don't know, like, I think JP, you're also, you think you can write a proof?
Yeah, I'm pretty sure I could write it up. I'm a lot more interested in some of the other problems though.
Right, right. So yeah, I don't know. Like if people, if any of you two are comfortable with writing the proof, you can put it in the PSI discussion. Otherwise, I'll put mine later. Okay.
Like
Yeah.
today only.
Sorry, couldn't hear.
You mean like we can give the proof by today?
If you can like write it now, like I think it'll just take a few minutes to write what we said. Um, do that.
Okay.
Yeah, in the PSI discussion, if you can just, if not like a whole proof, just if it's, even if it's sketch, that's fine. It just, I don't know, just, it feels like we completed something. That's
That's true.
it. So, shall we move on to the third problem? Or should we do the second one?
I've got some questions about the second one. Oh
Okay.
wait, I take it back. I have questions about the third one.
Okay.
I kind of feel like I might have overcooked the second one.
Overcooked. Okay. Okay,
But
so
there I think it would be helpful if I saw somebody else's elegant solution rather than going through my really draggy one.
mm-hmm. Why don't we start with the third one, and then we can go to the second one along with the four. Yeah. So let's just do the pick off the easy ones. So the third one is about the embedding of R1 into R2 by this map, which takes this T into this, right? And you have to prove that its image is one nappy of the hyperbola. Um, so yeah, of course, we have JP's probably almost their solution. Has anyone else tried the problem? I guess no. Then we can try it from scratch. So, JP, would you like to talk about like what's the kind of crux of your argument here?
So it's kind of two parts.
Mm-hmm.
The, the first part I did was to show that the image was the right half of the hyperbola, the part where x is greater than 0.
Mm-hmm.
So I just rewrote the problem as, or the mapping as being cosh comma sinh.
Right.
So we know that cosh squared minus sinh squared is 1. So that
Mm-hmm.
means that every point in the image satisfies the equation for the hyperbola. Since cosh is bigger than or equal to 1, that means that we only have the parts where x is bigger than or equal to 1.
Mm-hmm.
So that means that the image is in the right half of the hyperbola. But we also know that sinh, the y-coordinate, sinh is bijective. It's 1 to 1 and on 2. So that means that we're going to get all of the right half of the hyperbola. So,
Okay.
so that takes care of showing that the image is, not only is the image that right half of the hyperbola, but the mapping is 1 to 1. And of course, cosh and sinh are both smooth functions. The part I had trouble with is showing that it's an embedding, because I think the only thing we have to go on is the definition that says that it has to be a proper bijection, a proper smooth bijection. And the
Mm-hmm.
definition of proper is that the preimage of compact sets is compact.
Right.
So there's where I feel like I kind of went, well, I think I have a solution, but I don't think it's the best possible.
Well,
So
that's
suppose that we have a compact subset of the hyperbola.
right.
So since it's compact in Euclidean space, it has to be closed and bounded.
Mm-hmm. Hannibal.
So using continuity, I know that the preimage of a closed set is closed.
Mm-hmm.
So the preimage is closed. Since C is bounded, that means that it's going to lie between two horizontal lines. So the y coordinate is going to be between negative r and r for some r. Now, since sinh is a strictly increasing function, that means that the preimage is going to be between the arcsinh of negative r and the arcsinh of r,
That's clever.
which
Right.
shows that the preimage is also bounded.
Right.
So using Heine-Borel the other way around,
Mm-hmm. Mm-hmm.
the preimage is closed and bounded, so it's compact.
Right. And where are you actually unsatisfied with this proof? I think it's good.
It just doesn't. It feels overworked.
um, it feels overworked because this is just an hyperbola.
Yeah, I mean, it seems like it should just be obvious. I mean, I might be relying on my intuition about what an embedding means,
Mm-hmm.
but I'm thinking of things that aren't embeddings as pathological things, like the curve wrapping around the torus that we talked
Right.
about in class.
Right.
It's like, this isn't this. It's just a nice smooth image of hyperbola.
Mm-hmm.
There's nothing weird going on, so why are we having to work so hard?
I don't know. Probably because we're working with I think it's because of the compactness. The compactness makes it a bit non-trivial.
Another. Wait a minute.
Sorry?
I'm just thinking, is it obvious that the inverse map is continuous?
Inverse map, wait. The
Now, for it to be continuous, it needs to be the restriction of a continuous map from a neighborhood of the hyperbola to R. But if that's obvious, then we know that the continuous image of a compact set is compact.
Right.
Then we could appeal to that.
Yeah, and then you would have to go back to hyperbola. Yeah.
Yeah, that way we're not like slowly proving closed and bounded. So I wonder if that's true.
If the inverse,
so we know it's 1-to-1, since cinch is 1-to-1. Is the inverse is obviously continuous, but sometimes it's not easy to prove obvious things.
Right.
I mean, cinch is invertible, but cosh isn't.
Right.
Oh, but we don't need for them both to be invertible.
We don't.
No, because the inverse map is we just send a point on the hyperbola
to the
arc cinch of y.
Right.
And that is continuous on the function arc cinch of y is continuous on all of R2. So arc cinch y is the restriction of a continuous function on all of R2 to the hyperbola. Arc cinch is continuous.
Yes, okay.
And therefore it takes compact sets to compact sets.
Okay,
that's the easy
nice.
proof.
Yeah, okay.
That's the way I should have done it.
That feels good. Yeah. So the pre-image.
I'd like to suppress my second paragraph now and replace it with that.
Yeah, what was the pre-image again? The pre-image map, the inverse map takes you from the hyperbola to the arcsine of the y, right?
Mm-hmm. And the definition of continuous on a subset is that it's the restriction of a continuous function on a neighborhood of that subset in the ambient space.
Yeah, that. Sorry, can't hear you. You're really badly cutting out. Yeah, you can put it in the chat again. I'm looking at it. But yeah, so that feels like a very nice solution. Okay, can you hear me? So how does that boundedness make sense? Are you talking about the boundedness of this pre-image of C?
Yeah.
It is because what is it? C is bounded, so you have an R such that C is a subset of this. Now, because the hyperbolic sign is strictly increasing, what it means is that if you look at the pre-image of C, which is bounded, you'll get that it is a subset of this. And that means it is going to be also bounded.
Arcsign is going to map closed intervals to closed intervals in a one-to-one way.
Mm-hmm. Yes. Okay. That was problem 3. Ouch. It's really hard to
It sounds like
understand.
R2D2.
Yeah, you can use the chat. Sometimes you're fine, sometimes it's very hard to understand you. Okay, so that was problem 2. Problem 3. Very nice. Shall we check problem 5, the special linear group? That's, I probably think, that's like the middle line between problem 1 and 4. Like it's not too difficult, it's not too hard.
Yeah, in that list of errata, it pointed out that the hint referred back to the wrong problem.
There was a hint, right? I didn't see the hint. No.
Yeah, you didn't type in the hint, but it referred back to problem 5, whereas it should have referred back to problem 6 about homogeneous polynomials. So I didn't refer it specifically, but this lemma that I proved is part of the solution to problem 6 on homogeneous polynomials.
I see. Yeah, give me a second. Okay, so yeah, that's kind of how we should start it. So,
Cold out here?
so you
Taking the
proved this
laundry out.
lemma, right? So we have to prove that the n by n matrices with the determinant positive one form a group, which is the special linear groups. And you have to prove that this is actually a submanifold of the group of n by n. Submanifold of the n by n matrices, which form a manifold, and thus it's actually a Lie group. And if you go back to how we did the orthogonal group proof in Pollack, he gave the very nice example of how it is a Lie group. But yeah, I'm not sure. I'm pretty sure everyone else has seen the special linear group as a Lie group before. But I'd like to know if anyone else has any different approach to this. Because the problem is very simple enough. It is to just show that the n by n matrices of positive determinant 1 actually form a manifold, submanifold, right? And we can do it in probably a couple of different ways. Okay, then we'll try to go through this proof. Yeah. So you have proved the lemma, and then you have to prove the part 1 and part A. So the lemma he has is that if P is a homogeneous polynomial of degree m in k variables, then the set of points x where p of x is actually a, the k-1 dimensional submanifold of R, right? And you probably must have seen this before, but without proof. But yeah. So you have P of tx1 up until txk, and that gives you t to the m times P of x1 till x. Then you do the differentiation on both the sides, and you apply the chain rule, whatever you need to do the differentiation, and this is where you arrive. And if your t is equal to 1, what happens is you can write your MP in this manner. And this is very, if you get this, you probably know that you're in the right direction, because you can write this in the exact manner you write the tangent vectors. The notation is exactly the same. This is of course equal to the gradient of f times x, and that's equal to MP.
Yeah, I debated whether to use vector notation for the x's, but it became a mess, so I went back and took all the vector symbols out. Ooh. Oh no, that's right. That should be gradient P, not gradient F right there.
Oh yeah,
it should be gradient
it should
P
be gradient.
dot
Yeah,
X.
of course. There's no F.
Right.
And this one should be dpx, right?
Yeah, it all should be in terms of. Oh yeah. Yep.
But yeah, so that's where we arrive, and then if p of x is equal to a, which is non-zero, we see that if you take the derivative of pxx, and that is equal to the same thing. Yeah, gradient of p dot x, and that is equal to m a, because p of x is equal to a. So what happens is that the derivative of the this dpx from rk to r1 is actually surjective, and that's what we need to show, that a happens to be a regular value of p, and that the preimage is a submanifold. It works out. But yeah, I think the lemma itself is something that one uses all the time without proving it.
Yeah, it was just an exercise in the book. I didn't want to refer back to something that I hadn't proved.
Okay.
The exercise was a little bit more general. It's kind of a pretty problem.
Mm-hmm.
And that's to show that the all the manifolds with A bigger than 0 are diffeomorphic, and all the ones with A less than 0 are diffeomorphic.
Mm-hmm.
So the preimage of 1 is the same as is diffeomorphic to the preimage of 2, for example.
Right, right. So you prove the part A, which is the special linear condition. The determinant function of m of n, which is the unit diffeomorphic to Rn2, Rn squared, whatever, is a homogeneous polynomial of degree n in n squared variables, right? So SL of n is a submanifold of m of n, and its degree is going to be n squared minus 1. The other way we could have done this, is the way I would have done this, is like, I think it would be like, I don't know, unnecessary, but first construct GL, the general linear group, directly from the Euclidean space, and have it well defined, and like that is a Lie group, and then as the special linear group is going to be a subgroup of the general linear group, and then you can have the special, you can have it as a manifold, submanifold, and then if you can show that that's a submanifold of GL, then of course it's going to be a submanifold of M of n. Right? I think like that.
GL is an open subset of MN, right? GLN is just an open subset of MN.
GL, the general linear group is open in M of n, yeah.
Yeah, so it's still of dimension n squared, right?
Yep, it is open in Rn2, yep.
Yeah.
Yeah, but I think that's why I asked, like, how else anyone would try, but didn't get any answer. But like, that's how I would try whenever I see special linear group. I want to do something with the general linear group. Yeah.
That makes sense. There are other places where you go from something to the ones with determinant 1, right? Like ON and SON.
Yep. Yeah. Okay. Also, hello, Mika.
Oh, hello. I'm sorry for joining late, but I've been very busy. So how are you doing?
Yeah, we were trying to do the second piece at discussion.
Yeah, and which problem you are discussing right now?
We're discussing problem 5.
Okay, fine. Thank you.
Yeah. Okay, so that was part A. Now the part B is to show that, check that the tangent space to the special linear group as manifold is at the identity is all the matrices whose trace is going to be equal to 0. I think that's just like a computation at the linear algebra level, and that's probably what you did. The tangent space of SL at I will be the kernel of the derivative of the determinant map at the identity matrix, right? Now if you take an n by n matrix, then you take the derivative and apply that to that, you're going to get the derivative d over dt restricted to t equals to 0 of the determinant of I plus dA. Yes, okay.
That's just the definition of the directional derivative.
Right, yeah. The t equals to 0 thing, okay, yeah, makes sense. So this will be the coefficient of t and the polynomial expansion of this determinant. Yeah, and we know that the coefficient of s n minus 1 and the expansion of this determinant is minus of the negative of the trace of a. Because that's what the expansion will look like. So determinant of 1 plus ta is equal to q the n determinant of 1 over ti plus a, right? And then you try to expand this out. We're going to get minus 1 over t n minus trace of a times this, and it's going to continue. And you have to show that, and this shows that the derivative for a is equal to plus minus trace of a, and that's what we needed. So kernel is indeed the matrices a with trace equal to 0, because this is equal to the trace. So like the kernel is going to be all the things that take you to 0 trace. Okay, that was problem 5. I think we can get problem 6. There's nothing to talk about in problem 6. But yeah, I think there's nothing to talk about. I'll just ask others. Yeah, look at problem 6. And there's nothing really to do here, but yeah, just say if there's something you want to say about. So like, is everyone good with this?
For a book that's full of hard problems, this seemed too easy, like I must have missed something.
I agree, but like, okay, if we try to look at this again, you have a smooth function f defined in a neighborhood of a point, and you define the gradient to be the vector with all the partial derivatives, the usual way gradient works. Now, if you take a vector from Rn, and you try to show that the directional derivative dv is denoted by the gamma from a previous example, that satisfies the equation that dv of f is equal to the gradient of f with v. That is the standard inner product of gradient with the vector. So I mean, like for others, I can just ask the last part, like, do you understand like how the directional derivative is the dot product of the gradient with the vector? Like this is what you like take for, this is what you do in like early Calc 3 multivariable calculus. But yeah. So yeah, I mean that's pretty much what you have to show. That the directional derivative is this. I don't know, like I would just ask people at this point then, like, can someone tell me like why they use this d gamma v notation? If you have looked into the example, or if you have seen this before, what is the gamma and why do we need it?
Well, I'm sorry, I didn't see, I didn't even do the reading homework, but I think, yeah, but I think that when talking about a curve in the manifold, so the tangent would be like, yeah, the tangent would be like in something in like, yeah, the tangent will be like one vector, you see. I don't like, yeah, I don't know if you can get me, but the tangent is only one vector. Like,
Yep.
Yeah, it's like it's like let's just take the example of a sphere. So the tangent in sphere is a plane, but if we take a curve on this sphere, so it will be something like a circle,
Right.
and the tangent will be one vector, you see.
Yep.
And if we want, like, yeah, if we want to, like, and it's clear also that the directional derivative of the sphere with respect to this vector, it's the same as like the derivative with regards to this curve, which is a circle in this situation.
Right. So that's pretty much what I wanted. I mean, it's great, Mika. Thanks for the explanation.
Alright, cool. Yeah,
Right.
hopefully it helps.
Yeah, that's pretty much what I wanted. And this is what we see. You see when you do, what is it? The differential geometry in the curves and surfaces panel. Has anyone else taken something equivalent to that course? Doing curves and surfaces in a more sophisticated manner. Essentially using the book Carmel. That's pretty much it. But yeah, that's what Mika said was basically the point.
Oh yeah, totally. I've heard that. Yeah. No. So
Yes, I think here the Braden is still assuming that the manifold lives in some ambient space.
Yep.
But this is a way of defining what vectors are, is ways of differentiating functions.
Curves, right? Yeah.
Yeah, so take a curve, tangent vector is v, and then differentiate the composition.
So this is
And
the
then you have to deal with like equivalence classes of curves, blah blah blah.
Yeah.
Two curves are equivalent if they have the same tangent vector.
Right. So this is the example that the problem refers to. So he says if you take a point P and an ordinary n vector, the vector v in Rn, then you take this curve gamma v of t, which is defined in this manner, and then you have a tangent vector, as Mika said, d gamma v to this curve. And then the sphere example was really to the point. So if you have a tangent vector, then you want to find its coordinates with respect to the spaces, right? And what you do is you apply this tangent vector to this function f, and you get these. And here your a's are these derivatives of xi over dt when t is equal to 0, and as your xi's are basically going to be in the curve, so you have this, and so essentially you get at the end vi's, right, the components of the vector, and thus this directional derivative is equal to v in yep.
Yeah, I'm sorry for saying this, but I just want to go back to GPA6 answer about about this part, and I think that it's like I kind of don't agree with his answer, because I think that it's like like the first writing is the same as the second writing, while if we want to talk about the directional derivative, so we should take the
curve,
like the definition one, like
right.
like the limit one,
Yep,
which is because like these two formulas are absolutely the same.
the same.
But what but with the ambiguity or the difficulty is to derive this from the limit formula.
Mm-hmm.
Yeah, I agree. It was in the textbook that they did that part of the proof, so I just didn't repeat it. So the first formula I have
Thank you.
is taken from Braden. But since that's not the main book that we're using, that probably wasn't a good assumption.
Okay. I'm sorry, JP. Myself, I'm way behind in the reading. I missed the previous session, so maybe sometimes my comments don't make sense at all.
No worries. Glad to have you.
Okay. Thank you.
In fact, I'm counting on you to help clean up one of these other arguments that we've skipped. Or maybe two.
Mm-hmm. Okay. Yeah. Yeah, so that's basically problem 6. Yeah, so is everyone clear on that before we go on to the harder problems in the PSAT? Unjit and Cyan, are you good with us until now?
Yeah, okay.
Okay. Okay, so let's try to go into the harder problems, which is problems that we have left is problem 4 and 2. I don't think we'll be able to get to do problem 7. I'll leave that to the interest of the listener/reader, because it's a pretty hard problem from Hirsch. But we'll see problem 4 now. The problem 4 is this problem. It is, I think Oleg has a picture, so that can be helpful. Yep, so this is the problem. Post it in the chat. Yeah, so this is the stack of Recur's theorem, which says that if you have y as a regular value of f and x is compact, and has the same dimension as y. You have to show that the pre-image is a finite set, blah blah blah. Prove that there exists a neighborhood U of y in capital Y such that the pre-image of that neighborhood is a disjoint union, right? So this is, I think, like I also said it when we first saw it, isn't it? That this is very much like what we saw about the covering spaces, right? The sheets, the disjoint sheets you have on top of a base space, and that you use the covering map to, collapse all of that down. It looks a lot like that. But I think Mika wasn't with us when we did the regular value stuff. Do you want to just see the definition of regular value?
Oh, yeah. I just tell me which book, and I'm going to check it on my own. So I won't yeah.
Yeah. So we're doing Gilliman and Pollock.
I have that book. Yes.
Yep. So chapter 1, section 4, around the page 21, you will see a definition of the regular value.
Okay. Can you spell Paul for me, please?
Sorry, what? Couldn't hear.
Or can you spell the Paul for me? Pollock, like
P-O-L-L-A-C-K.
Oh, okay. Okay, got it now, yeah.
Mm-hmm. Yeah.
Okay, it's this one by Gilman and the Pollock, right?
Yep.
Okay. Around which page, please?
21.
Oh, thank you.
Yeah. So that is.
Yeah, I'm there.
Mm-hmm.
Okay. Yeah, you can continue with Divya. Like you don't have.
Yep.
So basically, the hypotheses here are strong enough to guarantee that the mapping is a local diffeomorphism.
Mm-hmm.
So around every point in the pre-image, there's an open set so that the function f takes that set diffeomorphically onto an open neighborhood of y.
Mm-hmm.
So that's what the regular value part gives you. Regular part, and they're the same dimension.
Right. I think that's what you're right. You first show that the pre-image is a finite set, y is a regular value. So for everything in the pre-image, there is going to be an open neighborhood such that f is going to map that neighborhood diffeomorphically onto this image, just because it's a regular value, right? And so you have the local diffeomorphism, which means that as f is 1-to-1 on each of these neighborhoods, so each of them is going to will contain exactly 1 point in the pre-image of y. Yeah, because you have the bijection. Yeah. So since these open sets together with the set the pre-image of y minus a point, okay, minus the point y, an open cover of the compact set X, there exists a finite subcover, each set of which contains at most 1 point in the pre-image of y. Let's try to unpack that. So you have these OIs, which are your open sets, and together with the other pre-image of y minus the singleton y.
So each OI contains exactly 1 point in the pre-image of y, little y.
Mm-hmm.
And then that other set, f inverse of y minus little y, contains everything except for the pre-image of y.
Okay. So you have a
So when you
point.
have a finite subcover,
Right.
the finite subcover probably contains that great big set, but then it's only going to contain finitely many of the OIs.
Mm-hmm.
And each OI contains one point in the preimage of Y.
Right. Okay. Yeah, that makes sense. So basically what you did was you said, okay, you have the local diffeomorphism. So each of these open sets have these xi's, these points. And then for the rest of x, what we can do is we can take the preimage of y minus the whatever you're taking the preimage of, and then take that the preimage of that, and that will give you the rest of what you need, excluding the xi. Okay, that's very clever.
Now the next step, here's a problem with the OIs.
Okay.
Two problems. One is that they might overlap.
Mm-hmm.
And the other one is that even though each OI contains only one of the x's, its boundary might contain other of the x's.
Okay. Mm.
So that made it more difficult for me to show that, or to figure out how to shrink those in order to guarantee that they're disjoint. Because we want the sets containing our xi's to be disjoint.
Right. Mm.
So I did that insert proof was to contain roughly this argument. So we've got a finite set of points, and we know that x is Hausdorff. So it might even involve an induction. We know that we can separate x1 from x2 using Hausdorffness. So now let's add in x3. We can separate x3 from x1 with open sets, and we can separate x3 from x2 by open sets.
Mm-hmm.
So if we take the two sets containing x3 and intersect them, then that will separate x3 from both x1 and x2.
Right.
And then you're basically going to have to ratchet that up, just intersecting all of these eventually to get a set, or to get sets which separate all of the xi's. So yeah, where it says insert proof, I think that it probably really does need a proof written down.
Okay. So.
Now, probably the simplest way, since we're working from Gilman-Pollock, is all of these guys live in some great big Euclidean space. So we could just take the minimum distance between any two of them, cut it in half if necessary, and then just take the open sets around them of that radius. But I was trying to come up with an argument that did not, use the ambient space. I wanted something that would hold for a general manifold rather than one embedded in Rn.
That'll be a bit hard, but I get it.
Well, that's where I think we have to use this Hausdorff condition.
Right. Because Pollock doesn't use the Hausdorff condition anywhere on like defining manifolds or anything.
Yeah, he doesn't need it because his manifolds live in Rn, so they get Hausdorffness for free.
Right. Right. Okay, so we have to prove that this is actually Hausdorff, right?
I don't think we have to prove that.
No, we have to prove that if you shrink.
We have to prove that we can separate these guys by open sets.
Okay.
So I know that each one is contained in an open set, which is diffeomorphic to a neighborhood of Y.
Mm-hmm.
But first of all, I need to shrink them so that these open sets are disjoint in X. And then after I do that, we need a single set in Y whose preimage is going to be these contained in these open sets that I'm calling O around each X.
Okay.
So it feels like, what it felt like to me is that we could just intersect the images, but based on Gum and Pollock's hint, that might not be correct. Because I didn't use that idea that f of that set X minus the union of the W's doesn't contain Y. Because it feels like he's using that. Map forward the complement, and then choose a neighborhood of Y that's not in that complement, and then take the preimage of that. But so far, what I do feel secure about, even though I haven't put all the details down, is that it is possible to find disjoint sets in X, each of which maps diffeomorphically onto an open neighborhood of Y. That I feel good about.
Right. I also feel good about that.
And there are finitely many of them, which means that we can take unions and intersections safely. The finite union of closed is closed, finite intersection of closed is closed, and same stuff with open. So we don't need to worry about, taking an arbitrary union of closed and it's no longer being closed. Junk like that.
Yeah, so like if you can show that by Hausdorffness, like each of these axes have open and disjoint neighborhoods that, along with the rest of whatever you had before, if they cover X, then you're done, I guess. Because that's what the O's help us with, right? They help us cover X. And if you shrink them, you have to check if they do cover X again.
Well, oh no, they certainly don't cover capital X.
No, I'm saying like O helps us with the rest of whatever we have F inverse of Y minus Y. Like, it allows for this to totally cover X. What I'm saying is if you shrink them, would you still have them cover X along with these?
See, if we map each of these OIs forward, we could give that a name. We could call those images UI.
The union of all of them.
So those UIs, the images of the OIs, each one of those is the neighborhood of Y, so that the pre-image is a set VI containing XI. So I'm reading from the statement of the problem. I mean, it feels like, well, why don't we just intersect all these guys? Why don't we just intersect the images of all the OIs? See, that's what I started writing there. The images F of OI are open neighborhoods. Just let U be the intersection of those. And then VI can be OI intersected with the pre-image of U.
Okay.
So that'll be a subset of that OI, so we know that it's a diffeomorphism. So why aren't we done? Why isn't that it? And I just have the gut feeling, especially based on the hint, that there's something wrong with that argument. I mean, I believe that each VI is going to be disjoint from the other VIs, because VI is contained in OI, and the OIs are disjoint.
Yeah, that's okay.
So I believe that these VIs, maybe it's that F inverse of U might not be equal to that disjoint union. Maybe the disjoint union is contained in the pre-image of U, but it's not everything in it.
It's okay. Can't you do that for the if instead of defining U as the intersection, if you define U as the union of all these images, wouldn't that also work? We would have U is equal to the union of FOIs, and VI is equal to the OI intersection inverse of U. But
Yeah, everything that I write after insert proof is just sketches of thoughts. Those things don't hang together. I'm trying to follow both my idea and respect his hint, and I'm not getting anywhere. I mean, if we do go to the hint, I feel like I've got the neighborhood's double use of I that he wants. I'm calling them OI, but that's because I thought I would do something to them and then rename them. Now I believe that F of that set is compact, because if I take X minus the union of the WIs, then that's a closed set, since the W's are open. And a closed subset of a compact set is compact. So X minus the union is compact, and then the image of a compact set is compact. Then I believe it doesn't contain Y, because the pre-image of Y is contained in the union of the WIs. So now what?
Right.
So, well, okay.
You sure that
That set is
happen?
compact and doesn't contain Y, so what do we do?
What do you do with that?
Since the image is compact, so it's closed. So that means that there's a neighborhood of Y in the complement. You could say, okay, we're going to let that set in the complement be our U or our V. And now if we take the that's our neighborhood U of Y.
Is the union of
And now,
Y's. No. Wait.
no, it's instead of doing it in terms of the images of the OIs, it's by looking in the complement of the image of X minus the union of the OIs.
Okay, the complement of that. That's going to be
An open set containing Y.
yes. Yeah, it's going to be an open neighborhood of Y. Try to take the pre-image of that. God.
And then we could do the same thing where we define VI to be the intersection of that pre-image with either WI or OI, however you're naming it.
Yeah, let's try that.
And then I could just declare that's the set. Those are the sets I'm looking for. But why do we need to do it that way rather than just by taking the intersection of the OIs? That's kind of why I'm giving up on it. Is I don't see what's wrong with my argument that's right about this one. So I feel like I'm missing something for sure.
Can you say that I think there could be like more than one way of choosing your V's for each X and Y. So yeah, more than one way of choosing U and VI's instead of each Y and X. But for each point, I probably think there's only one choice. I don't know. Can you in some way show that they're diffeomorphic, or like the same VI that you have here? Wait, what was the other one? It was the complement of f of x minus union of OI.
Yeah, that's the hint that they're giving. See, I'm mapping my open sets forward directly and just intersecting them. And he's mapping the complement forward and then choosing a set in the complement of the image of the complement. And it seems like mine is more straightforward. So if they're giving this hint, which is less straightforward,
There should be a reason.
I feel like there's a reason.
Do your VIs map diffeomorphically onto you?
I feel like they should because they're subsets of sets that map diffeomorphically.
Wait. You're saying OI maps diffeomorphically, and
Yep.
preimage of U's. Wait, the preimage of U. So wait, U is the intersection of all these open neighborhoods. You take the preimage of that. What is that going to be?
I feel like it should be a subset. It should be the union of subsets of the OIs, but I'm not positive about that.
Union of the subsets of the OIs.
Because is it possible that some points that aren't in any of the OIs might map into U?
Points that are not
I
in
mean,
OI.
nothing's going to hit Y. I know that.
Mm-hmm.
But could it hit some points around Y? Maybe.
God. Wait, so you're saying there is an X which is not in any of these open sets. You're going to say it's going to get mapped to some neighborhood of Y.
Sure. If you choose your neighborhood big enough, of course there'll be some points out there.
Right.
But by this construction, do we get any of those points? I don't know.
But wait, like if something is not in these OIs, like it is going to be in what? X minus the union of OIs, right?
Mm-hmm.
and the image of that is closed.
Mm-hmm.
So you're not going to get an open set. Wait. So, okay, let's just see. So if we have something like x prime is in x, capital X minus union of OIs in there. And we know that that is closed subset of a compact space, and it is compact. This continuous image under F is also going to be compact subset of Y. Yes. But, okay, so it's going to be, if you, wait, so f of x prime is going to be somewhere in f of capital X minus u of OI, which you say is compact. Yeah. But it's not closed, or is it closed?
Is what closed?
The image of X minus union of OI.
It is.
It is closed, right? Yeah, because continuous, right? So closed gets after closed.
No.
No? Wait.
Compact gets sent to compact,
Uh-huh.
and then compact will be closed.
Okay.
We're using compactness of X.
Wait, so this would be closed. Okay, so this is going to be closed in Y, and this is a neighborhood of f of little x prime, and if you take enough of these x primes, and if you take enough of these x primes, they're going to cover. Oh, no. Hey, what I'm trying to check is what is your f preimage of u, and how does that work with the diffeomorphism? Section of ones, if you look at the half inverse. Wouldn't
So I
that be
kind of
just
think I'm seeing why my construction using intersections is wrong. Because let's say that we're working with one-dimensional manifolds, and which of course would mean we're working with a circle, but ignore that. So suppose that we've found a set of x's or set of points x sub I in X, which map over to diffeomorphically to the interval from -1 to 1. So my point y is 0. So each one of those x's is contained in an open set which maps diffeomorphically onto the interval from -1 to 1. But there just happens to be another set which is mapped over to the interval from 1/2 to 1. There's nothing weird or wrong about that.
Okay.
So if I just intersect the OIs, or the images of the OIs, I'm going to get from -1 to 1. But when I take the pre-image of that, I'm going to get all those neighborhoods of x of I, but I'm also going to get that extra bit, which mapped into the part from a half to 1. So the pre-image of -1 to 1 will contain all these neighborhoods, which map diffeomorphically, but it might also contain some extraneous stuff. So I need a construction which is going to shrink it down to be from like -1/2 to 1/2 to make sure I don't get any of that extraneous stuff in there.
So that you can have diffeomorphism, right?
Well, I still have the diffeomorphism, but I don't have, other stuff that maps into this big neighborhood of Y. I only get the part which is coming from these neighborhoods of X.
Wait, then okay, so what's the problem in having all of that extraneous stuff then?
Because the pre-image of U is only supposed to consist of these VIs, which are the open neighborhoods of the X of I's. It's not the union of the VIs together with some other stuff, which we ignore.
Okay. Wait. Right, so you had to find the pre-image of U such that is equal to the union of VIs, right? But
Oh man,
what you
it's
have
something that I could draw. If we had a chalkboard, I could draw my counterexample pretty easily.
Okay, let me set up that whiteboard. This is an interesting problem. I'm very interested in this.
I'm trying to think of how to do it in words. It's really silly. You're going to have to post a link to it. I know we've done this before, but I forget.
Yeah. If this works, that's great. It should work. Let me see. Oh, ignore the wallpaper, that's why. Ah. Sometimes it just doesn't load. Why? God, this is going to load forever. No. Ah. Okay, I think I got this one. Oh no. God. Yeah, and that was a typo. So if I share this link to you, you can draw it, and others can join too. No. Differential topology.
Man, I'm sorry, I've been talking and talking, but I was muted.
Oh God, I thought you would finish the drawing and then talk.
Let me add one more label, then I'll come back.
Mm-hmm.
So my map from X to Y basically just wraps things around, but it also pulls this extra little section and doubles or triples up over on one side. Now, X does map, X has a neighborhood W1, which maps over onto a neighborhood of Y, so everything's great there. But the
Mm-hmm.
problem is that the pre-image of that set contains this little extra bit up at the top. So the pre-image of U contains a neighborhood of X, which maps diffeomorphically onto the neighborhood of Y, but it also contains extra stuff. So to make
Mm-hmm.
this work, I would somehow have to shrink this neighborhood down so that it didn't have this little part over there that overlaps.
Okay.
I don't know whether it's clear from my drawing, but Y is actually just a circle.
Right.
So where I've drawn this part, there's overlap in this section.
Mm-hmm.
But it maps down and then back and then down again.
Right, okay. Interesting.
So that's what we're having to avoid.
Yeah, the counterexample makes sense. But,
So, I mean, it's not truly a counterexample because this isn't a...
manifold.
At the points where,
Right.
yeah, where it turns around, it's no longer regular points. So these turnaround points are not regular values. Oh, but y is a regular value. The only problem is that we've chosen too large an interval around y.
So yeah, so that's your argument for, cutting the unnecessary stuff out.
Yeah, so my argument where I just said, let's just map the neighborhoods forward and intersect them, would not eliminate that.
Okay.
But maybe their way of doing it might. So they're going to take x minus w1. So x minus w1 is this closed set, which I'm going to make green here. My picture's a mess now.
Geometry is the
So
art of
this is the
making
x minus w1.
Right.
And then what is its image? It's going to, x minus w1 is going to contain all of this. Up to here, aha.
Together with...
So now if I choose a neighborhood of y and the complement of that,
it's going to...
it's got to be in here. And then its pre-image doesn't contain any of the extraneous stuff. So if I take the pre-image of that, that's strictly going to be contained in here.
Right. Okay.
So that must be why he's doing the hint.
That makes sense. Certainly.
So I understand from this why my construction doesn't work. But I don't know how. I guess now I'd be stuck on writing down, justifying why his construction does. I mean, it works for this picture, but how does it guarantee that the pre-image is contained only in the union of the W sub i's? Well, I guess it has to be, because the pre-image has to be contained in the complement of that complement.
Complement of x minus UOI. Union OI.
Right. Which would be, the complement of that would be the union of OI.
Yes.
So now we know that the pre-image is in there. So we just intersect it with each one separately. And we know that the function's 1-to-1 on each of those separately. That's probably enough. I guess I'm still a little confused, but I think I'm less confused than I was before.
Yeah, certainly that diagram and counterexample did help. And the whole discussion has been really amazing. I'm going to take a picture of this and... Yeah, it's been long enough that only we two have been discussing. What do others think about this?
Oh man, what a sad picture. It's at least as colorful. If my granddaughter did it, I'd put it on my refrigerator.
Wow, you need to teach your granddaughter all these things.
Well, she's 6 right now, so
Wow.
maybe she has a little while.
Okay, I feel good about this now than I did earlier. Maybe that's
Right?
fine. We can go on to problem 2.
After 40 minutes, now I understand his hint.
Right.
There's a bad typo in number 2 in what I wrote.
Oh.
Like
Okay.
early on, I have a limit, which should be the derivative at 0, not a limit.
DGU is it DG0?
No, here on the right, it's the derivative at t equals 0 of g of that. So there's a bunch of typos. So it should say,
Wait.
dg sub u of h is the derivative at t equals 0 of
Oh, okay.
what I have written there.
It's like you forgot to mention that restriction, right?
On the right where it says limit, it shouldn't say limit at all.
Okay, okay. It'll be, okay, the derivative, I see.
It should be the derivative at t equals 0.
Makes sense. So, this problem, part A, you have to check that the derivative is equal to v. Like, it looks very nice. But yeah, I'll have to do probably just some routine checking. But, you have this map. Takes you from U to U. Okay. You take a k vector. You take its derivative. This will be d over d t restricted to 0. From u plus dh to u plus dh. That will give you h, comma h. You take an x, you take a parameterization chart, take a neighborhood u of 0 in our case to a neighborhood f of x, and takes 0 to x, okay. Then you take p cross p to be a parameterization of x, comma x, as you would expect, and you have this nice chart transition.
More typos there.
V is
about halfway down the next line, it should be the derivative of the cross product at 0, 0. So
right,
that should be a subscript 0, 0.
Composition, yes. And that would be equal to taking the derivative and then crossing it with the HH and SLTV. Yeah, this is, this looks straightforward to me, and it was straightforward when I tried the problem too. I think the second one is a bit weird. The second one. The second one would be the diagonal map, which extends from this. So this is the delta is the diagonal map, and we have to show that the tangent space is the diagonal of you say that this map is actually a diffeomorphism of x onto delta. Okay, into the diagonal. Okay.
That actually is an earlier exercise from Pollock that I didn't prove.
I see, okay. But
that x is diffeomorphic to the diagonal of x cross x.
I think it is true. I just don't remember the proof, but I've seen it before.
It's true, but it's an exercise.
Yeah. Most of the things in Pollock are exercises. At least they're easy, not like a TIA. At least relatively easy, okay, we can say. You take, okay, dfx to this, tangent space of, okay, at point x to the tangent space of the diagonal at x, comma x. That's going to be a subset of this. We said this is a linear isomorphism. Yeah, because you have the diffeomorphism. And from part A, we see that the image of this map is precisely going to be the diagonal because of all this stuff. Okay, what do you think is bad about it? What happened is good.
I just wasn't sure whether we were supposed to have to do a diagram chase or whether there was an easier way to do part A.
You should be proud of doing a diagram chase. Like, that's the way math is done. Everything is diagram chase. But I mean, when you're talking about charts, I think you always have to do some kind of, chart transition. So
yeah, I guess maybe the question is whether we were supposed to use the fact that this lived in a big ambient space, or whether we were supposed to do it using charts.
Okay, so did we cover all the problems today? Yay, we did. Except
all
7.
All but 7.
Yeah, 7, I don't know. You gotta do it yourself. It's optional, that's why.
I can live without it.
It's a very interesting problem, nonetheless. Maybe you can try if you have time. But certainly, we tried all the 6 problems, and I haven't yet posted the PSET 3. I'll do it today. You'll have a week again, up until next Friday. But I don't know, how do people want it to be? Because if we just have one person submitting solutions, I don't know how helpful that is. But, how would you want the presets to be? And, if you want any kind of changes, I'm willing to make it.
Yes. Oh, so Divya, I would like to say something. Personally, I'm very interested in the course, but unfortunately, I don't have a lot of time, especially like the past week and the coming 2 or 3 weeks.
Okay.
So so it's really it's really hard for me. But I think that if we if there is no submissions for the PSETs, or maybe if there is only one submission or something like that, I think that it would be better if we keep working on the PSET together at the same time.
Okay. Yeah.
So this is my and if you don't mind, if there are not some people who are going very fast through the course, I think that others would be interested in going in maybe in slower paces, but in strong but in a strong way. So we cover everything, and we can we understand everything in a good way. So personally, I'm going to go I'm going to go through the exercises that I didn't do for the first PSET, and I'm going to try to do the reading and the other things, and then try for the second PSET. So anyway, this is my suggestion. And I also would like to ask GPA 6 one question. If you remember in Divya, it's about that exercise from the PSET 1, which is about the Zariski topology. I just want to ask him, how did he get the idea of the closure of that set? You remember that?
Yep, I have it here.
Yeah, it was a clever. I think that it was a clever choice. As far as I thought about it, I didn't get the intuition about about what the closure of that set would be. So yeah.
I was just thinking about the zero sets of polynomials. So, I mean, if you have a polynomial which is zero on an interval, it's got to be the zero polynomial. So I think I was just first thinking about it in terms of the behavior of polynomials.
Oh yeah, no.
So like if I had a polynomial of two variables and it vanished on an entire line, then that really restricts what that polynomial could be.
Yeah, now it's so like well, I don't know how it was.
But I didn't come up with the proof for a while. So yeah, I guess I don't have a good answer to your question because I had the intuition first, but then I had to work to get the proof.
Yeah.
But I did touch base with a friend of mine that I used to teach with, and I asked him whether that seemed right to him, and he agreed that that seemed like the right answer, but we didn't talk about the proof. I was trying really hard to get him interested in this class.
Yeah, I think
put a good bit of pressure, but he didn't join. He's retired also, so I was trying to find something that he'd want to join with.
Yeah, so yeah, I don't know. Like me and Divya talked about it the last time, and yeah, we said that it is an amazing and beautiful proof, and I asked it, like I said, yeah, it was really a clever choice to get odd real line, but now, like one word make it like something very obvious, in fact. Yeah, that's really amazing.
Yep.
Yeah, it's yeah, it was.
I do like your idea of slowing down a little bit and maybe doing even more problems, like more of the routine kind of problems.
Yeah, because I think that one learn better when thinking, or yeah, one learn better while thinking about problems and doing problems and getting the intuition behind every definition, theorem, and argument and things like that. Yeah. And also
so here's a
because,
question.
yeah, yes.
With your schedule, do you feel like you could commit to like one or two problems? Like we could still have a bigger set with like 6, but like, could you like if Dippy puts out the homework set today or tomorrow, maybe on Monday, could you say that you would do problems 2 and 5, or at least have sketches or ideas for 2 and a couple of problems?
That's something that I can't ensure now. So for example, I can say that I can do the last 2 problems from the P set 1. Yeah, I can say that because I have already done the reading related to that. But for these ones, I didn't like get it through the reading yet, and I didn't join you in the previous meeting also. And while doing the reading, I like most of the time I find myself lost, and how I read myself, my reading is like almost the same like doing the P set. So when I read something, I try to get the intuition behind it, and I try even to prove it and so on. So it takes time, like almost it takes time and effort, almost the same as the P set itself. But
I agree.
but personally, like what I can do with myself, like I don't mind if I'm way behind or something like that. But I'm trying to get everything done in the right way. So what I do, I keep like reading on my own and trying to think about things on my own. And yeah, that's what I'm looking for. In fact,
Okay.
I'm trying to upload everything on my mind. Yeah.
Right. So yeah, so kind of the suggestion is every time we have a P set, like what JP was trying to say was, don't try to like do all the problems, like how much of reading you have done, how much you can understand, pick those problems and try them. Like if like it doesn't matter, like if you do one problem or like 1.5, like at least if you can do one problem nicely.
You don't even have to do a problem. You just need to have like like a serious
approach.
how to say that, something like that, yeah, like
Mhm.
a serious essay on them or something like that.
Right,
yeah.
right.
Like a serious, let's say a serious draft.
Mm-hmm.
Right. Or even, when we meet to discuss, if you can say, I tried these things and they didn't work,
Mm-hmm.
at least we have
Exactly, yeah,
somewhere to
that's bad.
start.
Yeah, most of the time we end up learning some beautiful things while trying things and they don't work.
Right, right.
At least that happened to me. Like
Mhm.
I learned, I learned a lot of mathematics and I got a lot of good intuition and intuitive idea while trying things and they don't work.
Mm-hmm. Yeah. So that's kind of like what I would say. Like for the next PSET, just try to see if you can do like one problem, and don't worry about the others. That's fine.
Oh yeah, that's for
Maybe
sure. Yeah, I will. Yeah, before I will try to do the reading.
Yep.
Before the next meeting, and we will see. Yeah.
Yep. Yep.
Yeah.
maybe
So
on
thank
Monday
you
we
so much.
can each pick a problem or something so that we're not all working on the same one.
Right, right. So you can tell me. So when I put the PSAT, you can tell me which problem you're comfortable with working and which one do you think you can surely have a serious draft, right?
Oh yeah, that's a good idea. Yeah.
Right.
So we can keep in touch
Yep.
on on the yeah on the server here.
Yep. Yep. Yep.
Mhm.
Yeah. So that's what I recommend everyone to do, and so that we can have a more engaging and fruitful discussion every time.
Yeah, that's true.
Okay. Thanks for
So yeah,
staying.
so thank you so much. It was really nice meeting you, and yeah, I hope that we can. Yeah, we will get good discussion the next meeting.
Yep. 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 Okay.
Yeah, so thank you all, and yeah, you will finish the meeting right now, right?
Yep. Yep.
Okay, good. So yeah, take care.
Yeah.
See you.
All right. See everybody next week.
Yeah.
See
Yeah.
you. Yeah.
Thanks for staying.